KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we start with problem number 28. See here, first problem, that is 28 in this class. First I will explain you the problem, then we will go for answer. Okay, see here. A mercury lamp is a convenient source for studying frequency dependence of photoelectric emission. I will repeat once again. A mercury lamp is a convenient source for studying frequency of dependence of photoelectric emission, since it gives a number of spectral lines ranging from the ultraviolet to the red end of the visible spectrum. So he told that mercury lamp is convenient source for studying frequency dependence of photoelectric emission, and he is also giving the reason why it is convenient, because it covers from ultraviolet to the red end of the visible spectrum. Okay. In our experiment with rubidium photocell, the following lines from a mercury source were used. So we did one experiment. In that experiment with rubidium photocell, the following lines means these are 5. So the following spectral lines, following lines from a mercury source were used. Okay, right. So these are the lines they have given, and you check once again. It is what lambda 1 is equal to 3650 angstrom unit, lambda 2 is equal to 4047 angstrom unit, lambda 3 is equal to 4358 angstrom unit, lambda 4 is equal to 5461 angstrom unit, lambda 5 is equal to 6907 angstrom unit. Now, the stopping voltages respectively were measured to be, okay, right. So these are the stopping voltages values. One is V01 is equal to 1.28 volt, V02 is equal to 0.95 volt, V03 is equal to 0.74 volt, V04 is equal to 0.16 volt, V05 is equal to 0 volt. Okay, right. Now see here, determine the value of Planck's constant H. Next, B is estimate the threshold frequency and work function for the material. Okay, right. So he is asking to determine the value of Planck's constant H, small h, and right, estimate the threshold frequency and work function for the material. Okay, right. So what I am saying is here, first we are going to determine the value of Planck's constant. Okay, right. See here, determine the value of Planck's constant small h. B is estimate the threshold frequency and work function for the material. Right. First we are going to for A. See here, you know this formula, C is equal to nu lambda and nu is equal to C by lambda, right. We first determine frequency in each case and then plot a graph between stopping potential and frequency. Okay, see here. So these are the values for lambda. So in the bracket I mentioned because these values in terms of angstrom unit. Okay, that's why. Next nu is the frequency, and next V naught is the stopping potential. See here. So these values also given. Okay, that only I have written here. Okay, it is a table because this table helps us to draw the graph. Okay, right. See here. Here V naught versus V. So what is the graph V naught versus V, right? Stopping potential versus frequency. V naught versus V, V means here it is nu right? It is nu. Frequency is represented by nu, not V. V naught versus nu plot is shown in the figure, right? The first 4 points lie nearly on a straight line. The first 4 points lie nearly on a straight line which intercepts the nu axis at threshold frequency nu naught, which intercept the nu axis. This is the nu axis. Nu axis at threshold frequency nu naught is equal to 5.0 into 10 to the power of 14 hertz. Okay, this is the value. See here. The fifth point nu is equal to 4.3 into 10 to the power of 14 hertz. 4.3 into 10 to the power of 14 hertz, right? It is like points 1, 2, 3, 4, 5 like that. So these 5 points he is talking. The fifth point, the fifth point nu is equal to 4.3 into 10 to the power of 14 hertz corresponds to nu is less than nu naught. Because it is nu naught, it is nu. So this value is less than this value, So he is saying that nu is less than nu naught. So there is no photoelectric emission. When this is true, that is what, when nu is less than nu naught, when nu is less than nu naught, okay. So there is no photoelectric emission. There is no photoelectric emission, okay, and no stopping voltage is required to stop the current. No stopping voltage is required to stop the current. Okay, right. So once again I request you, please go through this table based on the given values and this formula. Afterwards we drew a graph, right, between frequency and stopping potential, and see these 5 points and see the scale on the graph. Here it is 2 hertz, right? 2 into 10 to the power of, it is in terms of 10 to the power of 14 it is like 2 into 10 to the power of 14 means it is 4 into 10 to the power of 14, 6 into 10 to the power of 14 like that. It is stopping potential in volts, it is 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, 1.4 like that. And when we drew a graph, we got 5 points, 1, 2, 3, 4, right? See here, I am telling you clearly, this is 1 point, it is on x-axis, second point, third point, fourth point, fifth point, 5 points are here, right? So from the graph what he is saying, that is important, which will give us Planck's constant, that only he is asking to find. Determine the value of Planck's constant small h, okay, right? See here. So when we are taking this graph, that is V naught versus nu is shown in the figure, the first 4 points lie nearly on a straight line, which intercept the nu axis, which intercept the, it is going to intercept, this line is going to intercept nu axis here, this is nu axis, right. At threshold frequency nu naught is equal to 5 into 10 to the power of, it is 4, it is 6, it is 5 into 10 to the power of 14 hertz. The fifth point nu is equal to 4.3 into 10 to the power of 14 hertz corresponds to nu is less than nu naught, okay. So it is the fifth point, here also you can see 4.3 into 10 to the power of 14 hertz, okay, right. When nu is less than nu naught, you can say that there is no photoelectric emission and no stopping voltage is required to stop the current, because there is no photoelectric emission, means there are no emission of electrons. When there are no electrons, when there is no emission of electrons, there will be no discussion about stopping voltage, okay, right. And here from this graph we are going to calculate slope of V naught versus nu graph, slope of V naught versus nu graph. You know very well, slope y by x, it is what, delta V divided by delta nu, right. So it is 1.28 minus 0, 1.28 minus 0, and here 8.2 minus 5.0, 1.28 minus 0 divided by 8.2 minus 5.0 into 10 to the power of 14. Okay, right. Complete this mathematical division. Finally, you will get it as 4.0 into 10 to the power of minus 15 volt second. This is because it is per second no frequency, and it is volt no. So when this goes to numerator, it is second no. So 4.0 into 10 to the power of minus 15 volt second. Next, from Einstein's photoelectric equation, right? See here. So from Einstein's photoelectric equation, observe carefully. This is the Einstein's photoelectric equation. That's Ke is equal to h nu minus W naught. Ke is equal to EV is equal to, you can write it as, V is the stopping potential ma. Ke is equal to EV is equal to h nu minus W naught. Okay, right. And here what we are writing, see this, E into delta V is equal to h into delta nu. E into delta V is equal to h into delta nu. Okay, right. How can we write this? That is what E into delta nu is equal to h into delta nu. When work function is constant, this is constant. When this is constant, in place of these two, you can write this one. When you are writing this one, mathematically you can write this step no. From this step, I can write this step no. Right? Just taking this one to here and taking this one to here. Now, see, it is what Planck's constant, it is what charge of electron. Okay. Finally, if we see, this is what h by E is equal to. H, we want to find h. E value we know, that is 1.6 into 10 to the power of minus 19. Okay, right. H by E is equal to, this one already we found ma. Delta V by delta nu already we found. Okay, so h by E is equal to this value, but we want to find h value, no, that is Planck's constant. No, Planck's constant h is equal to, Planck's constant h is equal to E into 4.0 into 10 to the power of minus 15, 4.0 into 10 to the power of minus 15, that is equal to, E value you write ma 1.6 into 10 to the power of minus 19, and 1.6 into 4 means 6.4, here already 10 to the power of minus 19, here 10 to the power of minus 15, total it is 10 to the power of minus 34 joule second, 6.4 into 10 to the power of minus 34 joule second. This is what Planck's constant. Okay, right. Next, B. See, A we cleared, that is what, determine the value of Planck's constant. Determine the value of Planck's constant. Okay, that we cleared. So which was we calculated as 6.4 into 10 to the power of minus 34 joule second. Okay, now B, threshold frequency. See here, estimate the threshold frequency and work function for the material, right. So first, threshold frequency nu naught is equal to, threshold frequency nu naught is equal to, right, that is what 5.0 into 10 to the power of minus 14 hertz, 5.0 into 10 to the power of minus 14 hertz. Next, work function, that is W naught is equal to, W naught is equal to. Okay, so when it is W naught, what will happen? That is W naught is equal to h nu naught. No, W naught is equal to h nu naught. Okay, W naught is equal to h nu naught, which is what threshold frequency is 5.0 into 10 to the power of 14 hertz ma, right. So just I corrected here, and work function W naught is equal to h nu naught. This value on threshold frequency here only it's present, right. So it is in joules ma, we can convert into electron volts. Okay, that's 1 joule is equal to 1 by 1.6 into 10 to the power of minus 19 electron volts. Okay, right. If you convert this value into electron volt, first you multiply ma, then you divide with 1.6 into 10 to the power of minus 19 to get the value in electron volt. Okay, then you will get it as 2 electron volts. Okay, I have written here 2.00. Anyhow, the final value, right, the final value regarding the magnitude is 2 electron volts. Okay, right. So in this problem we calculated, two things are there, A and B. A is determine the value of Planck's constant. Yes, we determine. Next, B is estimate the threshold frequency and work function for the material. Okay, right. Next question. See here, question number 29. The work function for the following metals is given. See, sodium, right, 2.75 electron volts, that is for Na, and K, that is what, okay, K is, it is 230 electron volt, and all are in electron volts. Here I didn't write electron volt, so I am saying, you please understand, this value is also in electron volt, and MO is also 4.17 electron volt, and nickel is also 5.15 electron volt. Okay, right. Which of these metals will not give photoelectric emission for a radiation of wavelength 3300 angstrom unit from a HE and CD, right? HE to CD laser placed 1 meter away from the photocell. What happens if the laser is brought nearer and placed 50 centimeters away? Right? They have given work function. Regarding this problem, they have given work function for some of the metals. Right? These are the values of work function. Now the question is, which of these metals will not give photoelectric emission for a radiation of wavelength 3300 angstrom unit from this laser placed 1 meter away from the photocell? Placed 1 meter away from the photocell. Okay, right. What happens? What happens if the laser is brought? What happens if the laser is brought nearer and placed 50 centimeters away? Placed 50 centimeters away. Okay, right. First, what is the wavelength given? 3300 angstrom unit. Just we are writing in meters. You know very well, 1 angstrom unit is equal to 10 to the power of minus 10 meters, right? So lambda is equal to 3300 into 10 to the power of minus 10 meters. Okay. Now, energy of an incident photon. So that's, E is equal to h nu, that is equal to hc by lambda. E is equal to h nu, that is equal to hc by lambda. It is h value, it is c value, it is lambda value, 3300 into 10 to the power of minus 10. Okay. It is what in joules ma. So you can convert into electron volts. I already told you 1 joule is equal to 1 by 1.6 into 10 to the power of minus 19 electron volt, right? If you convert this energy of the incident photon into electron volt, so you will get it as 3.75 electron volt. 3.75 electron volt. Okay, right. Now see here. That is what, after completion of this, after calculating energy of incident photon, now we are going to see, as the energy of incident photon is greater than the work functions, as the energy of the incident photon is greater than the work function of sodium and potassium, right, Na and K, but less than the work function of MO and Ni. MO and Ni. So the metals MO and Ni will not give photoelectric emission. The metals MO and Ni, right? Molybdenum and nickel will not give any photoelectric emission. Okay, right. Now next thing, if the laser is brought closer, intensity of radiation increases. Intensity of radiation increases, right? When intensity of radiation increases, you know very well, right? This intensity does not affect the result regarding MO and Ni, but the photoelectric current will increase for sodium and potassium with the increase in intensity. So one relation, the starting of this chapter, right? In theory, intensity is directly proportional to number of photoelectrons emitted. That is directly proportional to photocurrent, right? So because of taking that laser closer, right? If the laser is brought closer, intensity of radiation increases. Because of that, the photoelectric current in case of sodium and potassium will increase, but there is no change. Which this laser is brought closer means which does not affect the result regarding MO and Ni. It is same. What is same? What is same? The metals MO and Ni will not give photoelectric emission. Right? For this, what is the reason? I already told you here. That is what The energy of the incident photon is greater than the work function of sodium and potassium, but less than the work functions of molybdenum and nickel. That's why the metals MO and Ni will not give photoelectric emission. Okay, right. That only he is asking now in this question. First he is asking which of these metals will not give photoelectric emission for a radiation of wavelength 3000 angstrom unit from helium and cadmium laser placed 1 meters away from the photocell. The answer is MO and Ni. Next, what happens if the laser is brought nearer and placed 50 centimeters away? In case of potassium and sodium, photoelectric current will increase, but same as it is, MO and Ni will not give any photoelectric emission. Okay, right. Now, next question. See here, that is what question number 30. Question number 30. Okay, right. See here. Light of intensity 10 to the power of minus 5 watt per meter square falls on a sodium photocell of surface area 2 centimeter square. Full stop. Assuming that the top 5 layers of sodium absorb the incident energy, comma, estimate the time required for photoelectric emission in the wave picture of radiation, comma, estimate the time required for photoelectric emission in the wave picture of radiation. Full stop. The work function for the metal is given to be about 2 electron volt. What is the implication of your answer? What is the implication of your answer? Okay, right. So first try to understand the question. Light of intensity 10 to the power of minus 5 watt per meter square falls on a sodium photocell of surface area 2 centimeter square. Full stop. Assuming that the top 5 layers of sodium absorb the incident energy, right? Estimate the time required for photoelectric emission in the wave picture of radiation. First you have to calculate the time. Okay, the work function of the metal is given to be 2 electron volt, right? What is the implication of your answer, right? So finally we have to give the conclusion, right? See here. Suppose sodium has 1 conduction electron available per atom. Just suppose the sodium has 1 conduction electron available per atom, then effective atomic area is equal to 10 to the power of minus 20 meter square, which is approximately 10 to the power of minus 20 meter square. Okay, now number of conduction electrons in 5 layers, number of conduction electrons in 5, okay, number of conduction electrons in 5 layers. Okay, so number of conduction electrons in 5 layers, right? See here, so number of conduction electrons in 5 layers is equal to 5 into area of one layer. See here, area of one layer divided by effective atomic area. Okay, right. And you substitute the values, that is 5 into area of one layer means 2 into 10 to the power of minus 4, no? See, it is what, 2 centimeter square, we are converting into meter square, divided by effective atomic area, it is 10 to the power of minus 20 square meter, okay, meter square. So do this mathematical division, you will get it as 10 to the power of 17. 10 to the power of 17. Okay, right. Now intensity is equal, this formula already you know. Intensity is equal to energy by area into time. That you can write it as power by area. Now power is equal to intensity into area. Take these two. Power is equal to intensity into area. Incident power is equal to incident intensity into area. That is equal to incident intensity means what? They have given now 10 to the power of minus 5 watt per meter square, 10 to the power of minus 5 into area is this one now, that is what 2 into 10 to the power of minus 4, 2 into 10 to the power of minus 4, that is equal to 2 into 10 to the power of minus 9 watt, 2 into 10 to the power of minus 9 watt. This is the incident power. Okay. Now what I am saying is, see here ma, I didn't write here but I am saying, you just listen. In terms of wave picture, incident power is uniformly absorbed by all the electrons continuously. This is the statement we are getting from Einstein's information, the information given by Einstein regarding the photon picture of lights. Okay, that only he is writing here. I didn't write here but I am saying. I will repeat once again, please keep in mind. In terms of wave picture, incident power is uniformly absorbed by all the electrons continuously. Then you can write energy absorbed per second per electron. Per second per electron means what? It is a power. So energy absorbed per second per electron is equal to this value divided by 10 to the power of 17. 10 to the power of 17. Then 2 into 10 to the power of minus 26 watt. Now time required for photoelectric emission is equal to energy required per electron divided by energy absorbed per second per electron, that is equal to 2 electron volts divided by 2 into 10 to the power of minus 26 watt. That will give us 1.6 into 10 to the power of 7 seconds, that is approximately equal to 0.5 year. 0.5 year. Okay, and this value already given ma, this is what 2 electron volts. Okay, right. So now finally we are getting 0.5 year means half year, right? So nearly, that is what 365 days now 1 year means. So it is almost like 180 and 182.5 something, right? So because half of the year. So time required for photoelectric emission is 0.5 year. Okay, right. Now what is the implication? What is the implication you can give? Experimentally, photoelectric emission is observed nearly instantaneously, just approximately equal to 10 to the power of minus 9 seconds. But here it is what? Half of the year. Thus, the wave picture is in gross disagreement with the experiment. So whatever the wave picture is present here according to this question, which is a gross disagreement with the experiment. Okay, right. That is about 30th problem, third problem in this class. Okay, right. So in this class we discussed 3 problems, 28, 29 and 30. Okay, in our next class we will continue with 31st problem. Thank you.